So welcome to this lecture video of internal block diagram and pin diagram of IC555, operation of a stable multivibrator circuit using IC555 timer. So in this part A, we are going to discuss about the introduction of 555 timer, its application, its pin diagram and internal block diagram, and the operation inside 555 timer. What is going inside 555 timer? How it operates, so that we can use it in various electronics applications. So in 1971, it was introduced by Signet Corporation, and the main developer was Hans R. Kammersint. And from 1971 to till date, it has been highly used in various kind of applications because of its precise and highly stable delays of time and oscillation. And we can produce square wave of our desired time period. And for power electronics application, we need some time we need PWM, the pulse width modulation. We need the squared pulse to trigger the SCR. So for that, we can be, for the gate triggering circuit, we can use 555 timer. So op-amp can also be used for this purpose, but the 555 timer has an added advantage over this op-amp because of its cheap and reliable. And for this particular application only, it has some added advantage over op-amp. So apart from this, the triggering pulse generation that I have mentioned here, it can be used in the DC-DC converter. This is here. Apart from this, it can be used in the tachometers, analog frequency meter, voltage regulator, water level indicator, temperature controller, different measurement device, and there are n number of applications for this IC555 timer. Now here is the feature of the IC555. The 555 IC means the IC is the integrated circuit. So it has the voltage range of 5 to 18 volts. That means the supply voltage, one can use any voltage between this supply voltage range. It has the output current capacity of the 200 milliampere. It is called the sinking or sourcing of load current. It is 200 milliampere, and it can drive a load that is maximum value of the load current is 200 milliampere. And because of this high current value, it can drive a TTL, that is the transistor logic device. It has the maximum power dissipation of 600 milliwatt. Now we go to the next slide. In the next slide, here is the IC555. This is the IC, and there are total 8 pins, and we mark this pin like this. Here is a notch here. You can if you look the picture carefully, here is a notch here, so it is marked here. At the left hand side of this notch, from this left hand side of this notch, you can count 1 2 3, and there is a dot there for the convenience. Here is a dot there. From there you count 1 2 3 4 5 6 7 8, and the pin number 1, it is the ground pin. Pin 2 is the trigger. Pin 3 is the output. Pin 4 is the reset. Pin 5 is the control voltage. Pin 6 is the threshold voltage. Pin 7 is the discharge, and pin 8 is the power supply. And pin 8 is the power supply. Now in the previous slide, it was the pin diagram. Now here at the right hand side, look at the right hand side, it is the block diagram of IC555. When you are using it in a circuit, when you are drawing a circuit, you use this block diagram for convenience. Now there is a brief description about the pin. The pin 1, it is connected to the ground. Pin 2, it is the trigger pin. The output of the timer depends on the amplitude of the external trigger pulse at the trigger pin. So this trigger pin is very much important for generating the output of this IC555 timer. The pin 3 is the output pin. Pin 3 is the output pin, as we have discussed earlier. It can give up to 200 milliampere of load. Pin 4 is the reset. It is the reset pin. It can be used to reset the IC555, and to reset the IC555, it must be connected to the ground or the zero voltage, or or the voltage should be less than 0.8 volt. The pin 5 is the control voltage. It controls the pulse width of the output waveform, and pin 6 is the threshold. It sets state of the flip-flop, and depending on this pin, the state of the flip-flop that is inside this 555 timer, we'll discuss later, we can change the state. Pin 7, it is the discharge pin, and pin 8, it is the power supply pin. Now here is the schematic of the 555 IC, and as it is the integrated circuit. Inside the 555 timer, there is various transistors and diodes and resistors are there inside this IC555, and this could be grouped like this, and this could be grouped like this. Now look at this green portion. This is making a comparator circuit. This is making a trigger comparator. This one is a threshold comparator. This is a trigger comparator. This is a voltage divider circuit, and this is the flip-flop circuit, and this is the output circuit, and this is the discharge transistor. This is the discharge transistor that is placed there, and if we put it in a block diagram, we get this block diagram, and this block diagram is really very much important and very useful for knowing what is going inside the IC555 timer. Now consider this. Now consider here 3 resistance of 5 kilo ohm is connected in series, and one point is connected to the VCC and other point is connected to the ground. So this is making a voltage divider circuit. Okay, so this is making a voltage divider circuit. Apart from this, this one is a comparator, shown by the green portion. This is a comparator circuit. This is the flip-flop circuit, and here is the reset pin to reset the timer, and here is the discharge transistor. It could be used with some external capacitor to set the time period of the square wave. And here is the output. In this portion, there is a NOT gate there, just inverts the signal that is it is getting from the flip-flop and puts it in the output section. If we are putting a voltage of say some 5 to 15 volts here, so from 5 to 15 volts we are putting in the VCC point, and it is grounded here. So what will be the voltage at this point? The circled by the reading, the voltage at this node, it will be 2/3 of VCC, and the voltage at this point, it will be 1/3 of VCC. So just if you look carefully, this comparator, there are two terminals are there. One is plus, that is the non-inverting terminal, and another is minus, that is the inverting terminal. The inverting terminal is getting the voltages 2/3 of VCC, and the non-inverting terminal, it is connected to the threshold pin. It is the pin 6, the threshold pin. And consider this comparator. This comparator is one pin, that is the non-inverting input pin. It is connected to this point. That means it is getting 1/3 of VCC. Whatever VCC you are giving, this comparator is getting 1/3 of that voltage. And what is that other input of this comparator? The other input is the trigger. It is the trigger pin. So these are the input of the comparator, and now first consider how it is going to behave. Now consider this comparator and how it is going to behave. We will just see in the next slide. Now a brief recapitulation of what a comparator can do. Say here here a comparator is there, here a comparator is there. In this comparator, there are 3 terminals. These are 2 input terminal and 1 output terminal. In this 2 input terminal, one is the non-inverting input terminal, that is denoted as V plus, and another is denoted as V minus, that is the inverting input terminal. If the V plus is greater than V minus, then the V output would be in positive saturation. Then we will get the V0 is high. We can say V0 is high. And if the V plus is less than V minus, that means if this case happens, then we get the V0 is low. That means it is in the negative saturation. Now consider this case. We are putting a voltage of say 9 volt. We are putting a voltage say 9 volt in the VCC terminal, and so in this voltage divider circuit, what will be the voltage here at this node? It is the two-third of the VCC. So two-third of VCC means 6 volts here. And what is the voltage at this terminal, this node? This voltage will be 1/3 of VCC. That means 3 volts here. Now consider just this comparator, and we are putting a 7 volt in the threshold pin. We are putting a 7 volt in the threshold pin. So what is going to happen here? If we are putting 7 volt, that means the 7 volt is greater than 6 volt, then that means the non-inverting input terminal voltage is greater than the inverting input terminal voltage. The plus voltage is greater than V minus voltage. So the comparator output will be the high. That means the positive saturation. So it will be high. It is okay. Now consider the second case. If the threshold voltage has dropped below 6 volt. So what will be the comparator output? It has changed to low. Obviously, this voltage at the inverting input terminal is greater than this voltage, so the comparator output will be low. Now consider this comparator 2 at the bottom. Now look carefully. Here the 1/3 VCC at this point is connected to the non-inverting input terminal. That means the V plus terminal. And here it is connected, the trigger pin is connected to inverting input terminal. So in the inverting input terminal, if we are providing 5 volts, what is the voltage here? If this voltage is 9 volt, obviously this is 1/3 of VCC. That means here the voltage is 3 volt. Here the voltage is 3 volt. So the negative the inverting input terminal voltage is greater than non-inverting input terminal voltage. So the output will be low for this case. Now consider another case. That means if the trigger voltage it has dropped below 3 voltage, now it is 1 volt. So what will be the output voltage? Obviously it will be high, because the V plus here is greater than V minus, so it will be the high. The output of the comparator will be high. Now these two comparators are giving this comparator's outputs are getting inside this flip-flop, that the SR flip-flop. So what is going inside that SR flip-flop? We will first see the SR flip-flop truth table. So this is the SR flip-flop. So if the S equal to 0 and R equal to 0, and so this case, so if S equal to 0 and R equal to 0, then this Q pin it will not change, and again this will not change. So if we are putting 0 here and 0 here, then this will not change, no change. So no change at the right hand side. Now consider this case. That means if you are putting 0 at the S and 1 at R, so what is going to happen? You are putting 0 at S, means the upper comparator is low and the lower comparator is high. So if this is happening, then what will be the output? Then what will be the Q values? So look at the Q value. What is the Q value? Q value is 1. and this output, it is nothing but the inverted value, the inverted value there. That means this is 1. There's a q bar, that is, this means this is 1. So it will, if r is equal to 1 and is equal to 0, it will reset this flip flop. It will reset this flip flop. And what is the value of this one? If s equal to 1 and r equal to 0, then it will set the flip flop. Then that means the q value, the q is equal to 1. So obviously the q bar, it will be equal to 0. Now we have to consider this point also. You have to consider this point. If s equal to 1 and r equal to 1, then this is a forbidden state. You don't know what will be the output. This is undefined. So you don't know what will be the output. Now consider our case. Consider our case. So if we are putting a 0 voltage here, if we are putting a 0 voltage here and a 0 voltage here, that means that at trigger pin we are putting 0, and again here at the VCC the voltage is 9 volt. So what will be the voltage at this node? That is again 6 volt. At this node it will be 3 volt. So consider this comparator. At this comparator, at this comparator, this inverting input terminal is getting 6 volt. The non-inverting input terminal is getting 0 volt. Then obviously its output will be low. Consider this. Here it is 3 volt, it is 0 volt. Again, the non-inverting input terminal voltage is less than the is greater than the inverting input terminal voltage, then the output will be high. So that is mentioned here. So if s and r, that means this is 0 and this is r is 0 and s is equal to 1, then what is going to happen? Then q will be set. Q will be set, and what will be the q bar? Q bar will be low. So this is for the first row. Now what is going to happen for this? Consider the second case. That means if the pin 2 voltage, voltage at the pin 2 is increased to say 9 volts. So what will happen? So look at this comparator. This comparator has not changed. This comparator has not changed. The input at this comparator has not changed. So look at this input. It is 9 volt. It is 3 volt. That means the inverting input terminal voltage is greater than the non-inverting input terminal voltage. So it will force this comparator to low. Now there are two zeros. That means the state of that flip flop will not change. That means the previous state it was low. So it will be low in this state also. So it will be in this state also. Now look at the next case. So in the next case we are putting a voltage of 9 volt in the pin number 6. Now consider this. If we are putting 9 volt in this pin 6, what is going to happen? The non-inverting terminal voltage is 9 volt and the inverting input terminal voltage is 6 volt. So obviously the output of this comparator will be high, and this output of this comparator high means the RS flip-flop will change its state. Okay, so RS flip-flop, S equal to low, R equal to 1, that means the Q value will be 0. So obviously Q bar will be 1, that means high. So Q bar will be high. Now consider this case again. Consider the other case, that is the in the fourth column. In the fourth column, that is if this is 9 volt and this is 0 volt. This is 9 volt and this is 0 volt. Then both this comparator output will be high, and this is forbidden state and this is invalid. This is forbidden state and this is invalid. Now consider the case here. What is going here after this flip-flop? We got the input of the flip-flop and we got the output of the flip-flop, and what is going to happen after that flip-flop? Now after that flip flop, there it is directly it is directly connected to a NOT gate. Here is a NOT gate here. Here is a NOT gate here, and you get that output. That means when you are getting a high input, you are, that is inverted, and you are getting a low output. When there is a 1, you will get a 0 here. So we have discussed how we have discussed how this thing is operating. Now we have left few pins like the control voltage. Now look at the control voltage. It is connected to this pin, that is the inverting input terminal of this comparator. This is this pin. This is the control voltage of this pin number 5. That means it could be used to change the voltage level from 2/3 of VCC. That we have a better control. We could control the output of the 555 timer. Uh, After that, we get the reset pin. Again, in order to reset that, we have discussed earlier, the reset pin should be grounded, or the voltage at the reset pin should be below 0.8 volt. So if we want to reset that 555 timer, we have to close this switch in order to reset that 555 timer. Now apart from this, there is a discharge pin, that is a discharge pin, that is the pin number 7. Now look at the discharge pin. The connection is like this. There is a VCC, a resistance R, it is connected here, a resistance R, it is connected here, and a transistor is connected like this. A capacitor C is there. You choose the resistance and the capacitance value in order to charge or discharge the in order to set the RC value, that the in order to set the time constant, you can change the C and R value. Now say this VCC, it is connected in this way. At this point, at this node, it is the transistor is connected. So how it is operating, let us see. Say this this Q bar output is high right now. So this point is connected to this transistor. So this transistor, if the base signal is high, that means the transistor will switch on. Okay, the transistor is switched on. So transistor is switched on means the capacitor will discharge through this path. The capacitor will discharge through this path. Now say if the if here the Q bar is low, that means the transistor, the signal at the base is 0. That means the transistor is off. That means there is no connection. It should not discharge through this path. So what will happen? The capacitor will charge through this path. So the capacitor will charge through this path. So this is the way the different pin functions and the 555 timer operates. We'll further discuss how it could be used as astable, monostable, and bistable multivibrators in next lectures.